Hello, everyone. We are Group 6. Hello, everyone. We are Group 6. Our members consist of Harsh Patel, Jakku Samuel, and Saral Babu Shrestha. Today, we will be talking about 3D printed reactors. It is extremely important to optimize a chemical process and reactor design before it is fully implemented in an industrial scale. These optimizations could be a multitude of variables, including the flow rate of the inlets and the residence time of the components. Small-scale 3D printing reactors gives us the opportunity to test these parameters before the reactor models are implemented into full-size reactors. This saves time and money because through small-scale simulations, the ideal reactor design can be chosen from a variety of designs. The major topics covered in this lab are the design of the reactors through SOLIDWORKS, computer modeling through COMSOL, and the kinetics of the chemical reaction. In this experiment, malachite green reacts with sodium hydroxide. When malachite green reacts with sodium hydroxide, the reaction proceeds as a pseudo first-order reaction, which is displayed on the screen. The hydroxy group leaves the sodium hydroxide molecule and attaches to the malachite green. This reaction forms a colorless product, which can be seen in Figure 2. Another relevant value used for this experiment was the Pecklin number, which is calculated by the displayed equation, where L is a characteristic length of the reactor, V is the velocity of the flow, which is calculated by dividing the surface area by the fluid flow rate, and D is the diffusion coefficient, which is constant for all the trials. The lower the Pecklin number, the higher the mass diffusion. To achieve higher mass diffusion, the experiment should be run with a low flow rate. The chemicals used in this experiment were malachite green and sodium hydroxide. Malachite green and sodium hydroxide are skin and eye irritants, and are also unsafe to inhale or ingest. Malachite green is also a toxic chemical. To avoid any chemical hazards, we use the required PPE, which were lab coats, gloves, and safety goggles. If either chemical comes in contact with the skin or eyes, wash the affected area with water for 15 minutes. Also, when working with the 3D printer, make sure not to touch the resin right away, since it is extremely hot. If you touch the hot resin, apply isopropyl alcohol to the affected area and wash it with soap and water. Dispose of any chemicals into the hazardous waste container, which is labeled experimental waste. Dispose the micropipette tips into the sharps container.
These are the reactors we used for our 3D printed reactors lab. Figure 3 shows our T reactor, Figure 4 shows a diamond reactor, Figure 5 shows our long cylinder reactor, and Figure 6 shows our short cylinder reactor. We had to use COMSOL to find theoretical values of malachite green conversion, and to do this, several steps were necessary. First, we added water as a fluid to the reactor. Next, we added laminar flow, and the blue highlights show the two inlets of Mg and NaOH, and the outlet is shown at the bottom of the reactor. Next, we added transfer diluted species, where we plotted the concentration of Mg, NaOH, and the product. COMSOL assumes the diffusion coefficient of Mg, NaOH, and the product, which is fairly close to the actual values we are using. This inlet had a flow of Mg, with a concentration of 0.5 moles per meter cubed, and the other inlet had NaOH flow, with 100 moles per meter cubed. These are the reactions for Mg, NaOH, and the product. This is the velocity profile. As you can see, the flow is highest in the middle, and this follows the no-slip boundary condition. Finally, we can see the concentration profile for NaOH. As you can see, there is minimal mixing in the T reactor. These COMSOL modules are applied to the other 3D reactors, except for the cylindrical reactors, because of the complex helix shape.
First, create a model in SOLIDWORKS and 3D print it. Second, obtain the appropriate concentrations of malachite green for the calibration curve. Place 60 milliliters of malachite green in a syringe and 60 milliliters of sodium hydroxide in a syringe. Place the syringes in the syringe pump and the T reactor in the clamp. Connect the syringe and the inlets of the T reactor with rubber tubes. Set the appropriate flow rates in the pump, which were 15, 10, and 5 milliliters per minute. Start the pump and record the outlet product concentration for each test. Repeat this procedure for each 3D reactor model.
The calibration curve plots malachite green concentration versus the PC. This calibration curve will be used to determine the final concentration of Mg from the experimentally calculated PC. After calculating the final Mg concentration, the conversion of Mg can also be calculated. The calibration curve on figure 7 was used to find the Mg conversion of the T reactor, diamond reactor, and the long cylinder reactor. Figure 8 was used to find the Mg conversion of the small cylinder reactor.
We calculated the residence time by finding the volume of each reactor and dividing the calculated volume by the flow rate. After calculating the values, experimental Mg conversion was graphed versus the residence time. The diamond reactor had the highest conversion despite a lower residence time because the diamond helped mixing. The long cylinder had a higher conversion rate than the short cylinder due to longer residence time. We made a parity plot of the experimental Mg conversion versus the COMSOL predicted Mg conversion and added a 45-degree line to compare the values. Using the parity graph, we can compare the values of the theoretical versus experimental conversions. The T reactor was the closest to the 45-degree line, which means its experimental data was most comparable to the simulation data. The diamond reactor was the second most comparable, but it was still below the diagonal line, meaning COMSOL overpredicted the theoretical conversion. The long cylinder and short cylinder reactors were extremely below the diagonal line, which means it extremely overpredicted the theoretical conversion. This could be due to the complex helix shape of the reactor, which made it difficult for COMSOL to accurately calculate the values. We'd like to thank Chris, Adam, and Dr. Pascal for giving us feedback on this experiment. We'd also like to thank the Chemie department for hosting this lab.